This is the second lecture for Chapter 2 for ODE, and in this lecture I'll just state the existence of uniqueness theorems for the cases of the second order equations that we're discussing in this chapter, and then I'll go on to talk about linearity. The existence of uniqueness theorem for linear second order differential equations is essentially the same as it was for first order. You consider the second order differential equation here. In general, we're looking at initial value problem, and on the interval I, the functions p of t, q of t, and the forcing function h of t are all continuous. On that interval, there exists a unique solution for this differential equation, and that's basically the same thing as for the first order equations. In a linear differential equation, look at the coefficients in the forcing function, find the interval where they're all jointly continuous, and on that interval there exists a unique solution to this initial value problem. Now, with that quick existence and uniqueness theorem, we'll move on to linearity. So we had a principle of superposition for the first order equations. It holds for the second order. In fact, I wrote the principle in chapter 1 as though applied to a second order equation because it made the point better. But here it is in this situation. So you have a second order differential equation and you find two solutions, and you're going to be able to find two solutions that satisfy the equation. Again, we're working on linear ones right now. And these are homogeneous. Okay. So this is 0. Now if you can find two solutions, y1 and y2, both of them satisfying this differential equation, then the linear combination of them is also a solution. That's just basically that principle of superposition. Remember, it holds only for the homogeneous case. And now we're going to introduce a new idea, and that is a basis for a space, linear independence, and the basis for a space. The solutions, the idea is that you can assign a dimension of a space equal to the number of degrees of freedom. If you're looking at a plane surface, you have 2 degrees of freedom. You can go east and west or north and south, say. So you have 2 degrees of freedom. That's a two-dimensional space. For second order equations and for planar systems, those are also two-dimensional spaces. There's 2 degrees of freedom. Now, if within those 2 degrees of freedom you can find 2 linearly independent vectors or solutions, then every solution in that space can be written as a linear combination of them. So that's sort of the idea, and I think it's good to have a related mental image, which you already have. So here is the related mental image, and it's just the coordinate system. So you have I and j. You have your 2 coordinate vectors that make up the coordinate system. So what is I? I is, and j is 0, 1. These are linearly independent, which means that if you add them together, so you went c1 I plus some constant c2 times j, the only way this can be 0 is if c1 and c2 are both 0. You can't add 2 numbers together and get 0 without assigning 0 to the I component and 0 to the j component. Then every point in the space can be written as some combination, say 2i plus 3j. This is your c1 I plus your c2j. That's your linear combination. In this case, you assign coefficients, and then you have a plus sign, could be negative, and that's fine. So I and j are 2. You need 2 because it's a two-dimensional system. They're linearly independent. you have two linearly independent vectors in a two-dimensional space. They form a basis for the space. All points in the space can be written as linear combinations of them. Now these are not unique. Instead of J, could have used something else. For example, could have used, those are also linearly independent. They're not so handy. They're not so sort of minimalist. It's a little more complicated to use those two vectors, but they also are linearly independent. They form a basis, and you could write all the points in the space in terms of those two vectors. Now consider this other case. I'll have to clear this board for a second. Okay, so here's my two-dimensional space. Now let's let the first vector be, and let my second vector, which I'll just call y2 for no good reason, be, all right. These are two vectors in the space. They are not linearly independent. Basically, they are multiples of each other. y2 equals 3 times I. What can I represent? What points can I represent using these two numbers? The only thing I can represent are points along here. Whoops, on the line. I can't represent anything up here. That won't work. So by using these two vectors, I can represent some, but not all the points in the plane. So now we're going to write that same statement in terms of the solutions. So if we have two solutions, y1 and y2, of a second order linear homogeneous equation, second order is twice there, they can be taken as a basis for the solution space. So instead of representing all the points in a plane, we're now looking for all the solutions of the differential equation. So I find two solutions of the differential equation. I find that they are linearly independent. They constitute a basis. Then any solution of the differential equation can be written as a linear combination of them. And C1 and C2 are constants. So now the question is, first you'd have to find y1 and y2, and second you have to establish that they're linearly independent. So here is a statement of what it means to be linearly independent. If they're linearly independent, why can't I say that word? Then if I'm to add C1 times y1 plus C2 times y2, it will be 0 if C1 and C2 are not necessarily 0. If they are linearly independent, then C1 and C2 both have to be 0 in order for this to hold. That's pretty hard to show. I mean, sometimes you can recognize it, but there's a test, and it's called a Wronskian. And we can use it for functions. And here's a Wronskian. We have two functions, y1 and y2. Doesn't matter where you got them at this point. This is independent of the fact that they are solutions of a differential equation. We're only looking to see if they are linearly dependent or independent. The Wronskian is the determinant of a matrix composed of the functions y1 and y2 and their first derivatives. If the Wronskian is not identically 0 on the interval of interest, then the functions are linearly independent. The converse doesn't hold, and that needs to be stated. If the Wronskian is identically 0, does it mean that they are linearly dependent? No. There are examples of functions that are linearly independent, and yet the Wronskian is 0. So it doesn't rule it out, but it does rule it in. So here's an example. In this case, we will use solutions of a differential equation. So here's a second order differential equation, and there are two solutions that satisfy this equation, sine and cosine. And you can plug both of those into this equation independently, and they both will equal 0. Right? So are they linearly independent? So here's the Wronskian. So the Wronskian is composed of the functions. It's a determinant of the functions, y1 and y2, and their first derivatives. And you want to see if this equals 0, identically 0, on the interval of interest. Well, we have cosine sine, take the derivatives, take the determinant, and we find that that equals 1 for all time, actually. So the Wronskian is not identically 0. These two functions are linearly independent. There's two of them. It's a two-dimensional space. They form a basis for the solution space. All solutions can be written as linear combinations of these functions. So once you find these two, you can find all the solutions. Now, all of these combinations and these functions, they all solve the differential equation, but they don't all solve the same initial value problem. The values for C1 and C2 are calculated depending on those initial conditions. So these combinations solve the equation in general, but they do not solve the each initial value problem. So I want to show you one that doesn't work. So we had the same differential equation before, and now we can say that these two functions, sine t and sine 3t, they both solve that differential equation. If you put them in the differential equation, taking the second derivatives, adding them to the function, they'll equal 0. But you can see right off that they are multiples of each other. So if they're multiples of each other, they are not linearly independent. In fact, that's the whole idea. If they are linearly dependent, they are multiples of each other. But in case you didn't recognize that, you can plug it into the Wronskian just for practice. And here's a Wronskian again. This looks a little bit like the Jacobian, right? Remember the Jacobian? The Jacobian, though, would just be, say, it's a function of x and y and another function of x and y. So the Jacobian would be, or you can write it any way you want. You can put the g here or not, and then g by dx partial of g with respect to y, and taking the derivative. So you see there's kind of a similarity here. The Wronskian is the function itself, the two functions, and their first derivatives. Okay, so using this for these two functions, I end up with a Wronskian of 0. So they are solutions, but they do not form a basis. Some, but not all solutions can be written as linear combinations of them. Now I'm going to state Abels Theorem. It's not given in the textbook, but it's useful, and we will use it in finding some solutions. Okay, so again, we're starting with a second order linear differential equation, and we have some interval I where P and Q are continuous. This is a homogeneous equation. And now we're saying that the Wronskian of these two functions equals some constant c. C doesn't depend on time, and actually it can be fairly independent, just can't be 0. Say c is non-zero. E to the, this looks a little bit like what? Looks like the integrating factor, doesn't it? Okay. Multiplied by c equals a Wronskian. You can work this backwards to find another function, y2. And that's what we'll do with it. We'll set up the Wronskian, we'll make it equal to some constant, non-zero constant, which we can set equal to 1, e to the minus the integral of the coefficient of y, the first derivative, and then we'll be able to find y2, and that y2 will be linearly independent. Right, we'll see how this works. I'm not presenting this with any derivation. I just wanted to present it here because it's a tool that we'll use, and I try to put all the tools in this second lecture. Here. Now for the non-homogeneous equations, we again, as in the case for the first order equations, we have two extended linearity principles. and I'll just write them here just for review. So we have a second order differential equation, and we find two solutions for it. One is called a particular solution. The particular solution is a solution of the differential equation with a forcing function h of t as it's written. Then we can find a complementary solution. That's a solution of the same differential equation with h of t set equal to 0. The first extended linearity principle states that the sum of the complementary solution, actually any linear combination of the complementary solution, and the particular solution is also a solution of the differential equation. The reason for that is when you put this through the differential equation, all the derivatives and the functions of the complementary equals 0. Y of p equals h of t. 0 plus h of t is equal to h of t, the forcing function. So this is the same principle as before. And again, we have the second extended linearity principle. If the forcing function is some combination of functions, then the particular function can consist of several small, so to speak, particular solutions, each one attached to one of the h's. Then you can add them all up together, and that will be your particular solution. Now this is extra reading, optional reading on the derivation of the Wronskian, but I'll just go ahead and write it out here, because if you have an interest, if you have no interest, then don't worry about it. It's not part of this class. I'm just want to present it here because it makes Wronskian not so mysterious. Let's say I have two functions, y2 and y1, and say they are linearly dependent. Then they are multiples of each other. So assuming they are not 0, and I divide them by each other, I will get k. This is y1 of t and y2 of t. Again, I'm assuming y1 and 2 are not 0. So they're equal to a constant. If they're linear multiples of each other, then somehow I can write them as a constant. Now I'm going to take the derivative, and I'll have to use the quotient rule. So when I use the quotient rule, in the numerator I have y1 times dy2 dt minus y2 times dy1 by dt, remember low d high, high d low and all that, divided by y1 of t squared. And taking the derivative of k, it's going to be 0 because that's a constant. Now in order for this to hold, remember y1 is not 0, so the numerator, which is good, don't have to worry about that, so the numerator has to be 0. That means y1 dy2 by dt minus y2 dy1 by dt has to be 0. This is for linear dependence. Okay, what does this look like? It looks like the derivative of a matrix. You could put the y1 here and dy2 dt here, and here's your y2 and dy1 by dy2 by dt. I'm sorry. This is the Wronskian. Now, it could equal 0 or not. If these are linearly dependent and then they are equal to a constant, this will be 0. If this is not 0, then we know that this did not hold. There can be other situations in which this Wronskian is 0 and the functions are still linearly independent. But if it is 0, if it is not 0, it definitely cannot, that this cannot hold. So if it's not 0, we know that they are linearly independent. But it doesn't rule out there are other cases in which they are linearly independent and yet the Wronskian is 0. So I just wanted to show you that, just sort of a derivation of the Wronskian, so you say, where did anyone come up with this?